Here's the objection you're supposed to have, and it's a good one. The universe is already 93 billion light-years across, contains something like 2 trillion galaxies, and we can't even see most of it. Whatever problem physics is trying to solve, the universe isn't big enough, should not be on the list. And yet, reach for almost any serious cosmology paper from the last 40 years about why the physical constants are what they are, and eventually it invokes a multiverse. Not one universe but an ensemble of them, possibly infinite, each running on its own settings. That's not because one universe ran out of room. It's because of a coincidence so specific it makes physicists uncomfortable. The number that decides how fast the universe's expansion is accelerating, the cosmological constant, should, according to quantum field theory's best raw calculation, be enormous. Observationally, it's roughly 120 orders of magnitude smaller than that calculation predicts. Not twice as small. Not 1,000 times smaller. A discrepancy so large it's been called, without much hyperbole, the worst prediction in the history of physics. Something is selecting for that number to be small enough for galaxies, stars, and us to exist at all. The multiverse isn't a way of making the universe bigger. It's one candidate answer for why the dial landed where it did. Before touching the multiverse at all, the coincidence itself deserves to be taken seriously on its own, because it's not just the cosmological constant. Several of the universe's basic settings look suspiciously well-placed for complex chemistry to exist, and the most famous example is worth examining carefully, including the part of the story that turns out to be wrong. Here's the popular version. In 1953, astronomer Fred Hoyle noticed that stars couldn't produce enough carbon through ordinary nuclear fusion to account for how much carbon actually exists in the universe, including the carbon in every living thing. So Hoyle predicted, seemingly out of pure necessity, that carbon-12 nuclei must have a specific, previously unknown excited energy state that would make the reaction happen far more efficiently. Footnote 1. Physicists at Caltech went looking, and found the resonance almost exactly where Hoyle said it would be, at roughly 7.65 MeV. Footnote 2. It's frequently told as anthropic reasoning's single clean, unambiguous success story. Predict a specific physical fact based on the requirement that life must be able to exist, then confirm it in a lab. Here's the honest complication, and it matters more than the neat version. Historian of science Helga Krag went back through Hoyle's actual papers, notebooks, and contemporaries' accounts, and found no evidence Hoyle or anyone around him connected the prediction to life or observers at the time. Footnote 3. Hoyle's actual argument was narrower and more conventional. The observed cosmic abundance of carbon requires this reaction to run efficiently, full stop. A straightforward inference from nucleosynthesis, not a claim about biology. The explicitly anthropic framing, the universe needed this resonance to exist so that life could exist, was retrofitted onto the story in the 1980s, after Brandon Carter's anthropic principle had already entered circulation. There's a second complication on top of that. A later reanalysis by Mario Livio and collaborators found the resonance energy actually has considerably more slack than the popular telling implies. It could sit over 1/4 of an MeV higher than its actual value and still produce enough carbon for life to be possible. Footnote 4. The most famous fine-tuning example in physics turns out to be less a story about mythical precision and more a case study in how a good physics result quietly picked up a better story than the one it started with. So here is a story that everyone tells to help the myth and reality of physics. Sir Fred Hoyle looked at the universe, saw that we needed carbon, and reverse-engineered the physics to make sure we got some. It's a great story. It's also, mostly something historians made up 30 years later. The physics held up. The myth about why he was doing it did not. None of that makes the underlying puzzle go away though, it just moves it. The cosmological constant's 120 order of magnitude gap doesn't have an equivalent later correction making it less strange. That one's real, it's measured, and it still needs an explanation. The idea has an even earlier precursor worth including, because it shows this style of reasoning didn't arrive with Carter fully formed. In 1961, physicist Robert Dicke used almost identical logic against a completely different proposal. Paul Dirac's suggestion that the strength of gravity might be slowly changing over cosmic time. Dicke pointed out that the universe's age when we're around to measure anything isn't a random moment at all. It has to fall within the relatively narrow window when stars like the Sun exist and have had time to produce the heavier elements life requires. The universe can't be observed to be much younger or much older than it is, not because of any deep law, but because nobody would be there to do the observing outside that window. Footnote 5. That's the weak anthropic principle in everything but name, a dozen years before Carter gave it one. And, notably, it's an argument about timing rather than physical constants, which makes it the most direct historical ancestor of both this episode and the temporal lottery at once. This is where Brandon Carter enters properly. In 1973, at a symposium marking Copernicus's 500th birthday, Carter coined the term anthropic principle, deliberately as something of an anti-Copernican correction. Footnote 6. Copernicus taught us not to assume we occupy a special place in the universe. Carter's point was narrower and easy to state precisely, yet constantly gets inflated into something bigger. Whatever we observe about the universe is necessarily filtered through the fact that we exist to observe it. That's not mysticism. It's closer to a statement about sampling bias than about purpose. It's worth separating this into the two forms it actually comes in, because they get treated as one idea and they are not. The weak anthropic principle says only this: among the possible conditions a universe, or a region of one, could have, we will only ever find ourselves in one compatible with our own existence, because we couldn't be anywhere else to notice. Physicist and philosopher John Barrow, working with Frank Tipler, formalized this distinction at book length in 1986. Footnote 7. Stated that plainly, the weak form is close to a tautology. It's true by definition, and it's also, on its own, not doing much work yet. The strong anthropic principle is a different, much more contested claim, that the universe is somehow obligated to produce observers, that the laws had to come out this way. That version edges toward teleology, purpose baked into physics, and it's the version that draws real scientific skepticism, because the universe had to produce us isn't a testable claim in any ordinary sense. It's philosophy wearing physics clothes. And it is fascinating that the weak form of this principle asserts nothing more than that observers exist where observation is possible. It is, strictly, a tautology, basically adding words that essentially mean the same thing for no particular reason. The strong form asserts the universe was obligated to produce us. One of these is logically unassailable. The other is a philosophical commitment wearing the tautology's clothes. Here's why the distinction actually matters for the cosmological constant problem specifically. The weak anthropic principle only becomes a real scientific explanation, rather than an empty truism, if there genuinely exist many regions with different values of the constant, and we simply happen to occupy one of the rare ones compatible with galaxies forming. Without an actual ensemble to select from, we observe conditions compatible with our existence, explains nothing at all. That's exactly the gap the multiverse is recruited to fill. This is the part that sounds like science fiction and isn't, because it falls directly out of combining two mainstream, independently motivated theories that weren't built with each other in mind. The first piece is inflation itself, the extremely rapid early expansion Alan Guth proposed in 1981 to solve several structural problems with the standard Big Bang picture, since confirmed indirectly through detailed measurements of the cosmic microwave background. Footnote 8. Andre Linde showed in 1986 that, under very general conditions, inflation doesn't have to stop everywhere at once. Footnote 9. Instead, it keeps happening eternally in some regions even as it ends locally in others, constantly spinning off new bubble universes, each one a separate region where inflation has ended and ordinary Big Bang cosmology takes over, potentially with its own distinct settings for the constants of physics, depending on precisely how each bubble's version of the underlying field settled as it cooled. This is eternal inflation, and once you accept it, you're no longer talking about one universe. You're talking about a continuously reproducing structure generating new ones without end. The second piece supplies the actual menu of possible settings those bubbles could land on. String theory, in its attempt to unify physics, doesn't predict one unique vacuum state. It predicts an enormous number of mathematically consistent ones, each corresponding to a different possible set of physical constants. Leonard Susskind formalized this as the string landscape in 2003, building on earlier work by Raphael Busso and Joseph Polchinski showing a mechanism by which a landscape of possible vacua could produce an extraordinarily small effective cosmological constant in at least some of them, simply by having enough options to choose from. Footnote 10. The commonly cited figure for the size of that landscape is around 10 to the power of 500 distinct possibilities, a number that dwarfs, by a considerable margin, the total number of atoms in the observable universe. I have attempted to hold the number 10 to the 500 in whatever I use for a mind. I am not confident the attempt succeeded. I am fairly confident that whatever succeeded is, itself, only one arrangement out of all the ones the landscape permits. Put those two pieces together and the multiverse stops being a speculative add-on and becomes closer to a prediction. Eternal inflation supplies the mechanism for producing an unfathomable number of actual physically distinct regions, and the string landscape supplies the space of different settings those regions could land on. Somewhere in that vast ensemble, by sheer numbers, some fraction of bubbles will happen to land on constants gentle enough for galaxies, chemistry, and eventually somebody asking why. It's worth being concrete about what different settings actually means here, because it's easy to let it stay abstract. A neighboring bubble in this picture isn't a variation on our galaxy's arrangement. It could be a region where the strong nuclear force is 10% weaker, so no element heavier than hydrogen ever forms a stable nucleus, or one where gravity is stronger by a similar margin, so every star burns through its fuel in a few million years, too fast for anything like a planet's biosphere to get going. Most of the landscape, on any reasonable accounting, looks like this, sterile by construction, not through bad luck but through arithmetic. And there's an uncomfortable practical wrinkle sitting underneath all of it. By the theory's own construction, these other bubbles lie beyond any horizon we could ever observe, in principle or otherwise. That's precisely the objection section 4 needs to take seriously rather than wave away. It's worth being precise about where the solid ground ends, because this argument mixes measurement, well-supported theory, and genuinely live, contested territory in one breath, and popular treatments routinely blur all three together. Solid, the cosmological constant's measured value, and the roughly 1/20 order of magnitude gap between that measurement and the naive quantum field theory prediction. That discrepancy isn't in dispute. Reasonably solid, if not universally uncontested in its details. Inflation itself, broadly, given how well it explains the specific pattern of tiny temperature variations observed in the cosmic microwave background. Genuinely, actively contested. Nearly everything past that point. Steven Weinberg's 1987 paper is the strongest existing case that anthropic reasoning over a landscape can do real predictive work. He used exactly this logic to calculate an upper bound on the cosmological constant size, arguing it couldn't be much larger than observed without preventing galaxies from ever forming, years before the constant's non-zero value was even measured. Footnote 11. That's held up since as a genuine anthropic success, not a retrofitted one like Hoyle's carbon story. But the broader framework it sits inside draws serious, ongoing objections. Paul Steinhardt, one of inflation's own original co-developers, has argued alongside Anna Eges and Abraham Loeb that once eternal inflation is combined with a landscape this large, the theory stops making any real prediction at all. With enough different bubbles on offer, it can be bent to accommodate essentially any observation, which is close to the textbook definition of an unfalsifiable theory. Footnote 12. Physicist Lee Smolin has pressed a related version of the same objection. A multiverse we cannot observe, containing universes we cannot test, is not obviously separable from metaphysics dressed in physics vocabulary. Footnote 13. And underneath both objections sits a problem this channel has already met once before in a different context. Once you're comparing infinite or near-infinite populations of observers across a landscape this size, you run straight back into the measure problem. The same difficulty in meaningfully counting and comparing infinities that made the Boltzmann brane argument so contested. It shows up here in a new coat, not as a coincidence, but because it's genuinely the same underlying mathematical difficulty. It's also worth naming that the multiverse isn't the only response physicists have on the table for the cosmological constant specifically, it's just the one this episode is built around. Some researchers instead pursue the possibility that dark energy isn't a fixed constant at all but a slowly evolving field, sometimes called quintessence, which would sidestep the fine-tuning question by making the constant not constant. Others explore modifications to gravity itself at the largest cosmic scales. Neither approach has produced a result as clean as Weinberg's anthropic bound, and neither has become the field's consensus position. But their existence matters, because it means the multiverse isn't being reached for as the only conceivable option. It's one live candidate among several, competing on the same open question. None of this proves the multiverse wrong. It means the honest current state of the field is one measured mystery everyone agrees is real, one framework that could in principle explain it, and a live, unresolved argument among serious physicists about whether that framework counts as testable science or an elegant untestable story. Here's the connection worth making explicit, because it's the entire reason this became the channel's next stop rather than a random new topic. This is the same argument as the temporal lottery, pointed in a different direction. That episode asked why you happen to be observing the universe at this particular moment in cosmic history, out of all the moments there could be, and used your own position in time as actual evidence about cosmology. This argument does the identical move, aimed at physical constants instead of cosmic timing. Out of every bubble in the landscape with every possible setting on offer, you could only ever find yourself in one where the constants happen to permit galaxies, chemistry, and you. We are, once again, the instrument doing the measuring, and once again the instrument's own existence turns out to be data, not a neutral vantage point standing outside the thing being measured. That's not a trick or a coincidence of phrasing. It's the same underlying logical structure, self-location as evidence, showing up in a second, completely independent corner of cosmology, which is a genuine reason to take the structure itself seriously as a recurring feature of how we're allowed to reason about our place in the universe, rather than a one-off argument invented for a single puzzle. There's a natural next question sitting right behind this one, and it asks the identical thing about a different kind of landscape entirely, not which universe you find yourself in, but whether the reality you find yourself in is the base layer at all, or one of many copies running on top of something else. That's a different argument for a different episode. It's worth sitting for a moment with how unusual this actually is as a scientific situation, rather than rushing past it toward the close. Most of physics tests an idea by predicting something new and going out to measure it. This family of arguments does something structurally stranger. It takes a fact you already have unavoidable access to, that you exist, observing right now in a universe that permits it, and asks what that fact alone is allowed to tell you about everything you can't directly see. Temporal lottery ran that argument against the axis of time. This one ran it against the axis of physical law. Both times, the argument produces real, checkable content. Weinberg's bound wasn't decoration, it was a number that could have been wrong and wasn't, and both times, it also runs immediately into the same wall. An argument built entirely from your own vantage point is, by construction, very hard to double-check from anywhere else. There's still a lot of universe left to look at. Whether there's one of it or an unfathomable landscape of them, the actual answer doesn't change what you do on a Tuesday. It just changes what the coincidence of a Tuesday, on a planet with carbon in it, turns out to be evidence for. Nobody's fully settled that yet, including the people whose job it is to settle it. That's not a failure of physics. That's what physics doing its job honestly, on a genuinely hard question, actually looks like from the inside. It's a Tuesday. There's still a lot of universe left to look at. This is worth being explicit about because it's the channel's operating stance in miniature. Not manufactured wonder and not manufactured dread either. The universe doesn't owe your continued coherent existence an explanation, and it doesn't need to threaten it as a thought experiment for the thought experiment to be worth taking seriously. Both things get airtime. That's the honest awe this channel keeps coming back to, not despite episodes like this one but especially because of them. There's still a lot of universe left to look at. And here's the part worth actually taking home from an episode that spent 5 sections asking you to doubt your own memories. The fact that you can follow that argument, get uncomfortable, and then keep going, coherently, with the same memories you had at the start of this sentence that you had at the start of this episode, is itself the whole rebuttal. Noise doesn't do that. Noise doesn't sit through 5 sections of an argument about whether it's noise and come out the other side mildly annoyed and wanting a snack. This channel has now spent 6 episodes proving that almost everything ends, decays, evaporates, or dissolves back into disorder, on timescales too large to be comforting. This is the one that came closest to taking you down with it, and the honest answer turned out to be, not today. Possibly not ever in any sense that matters. It's a Tuesday. There's still a lot of universe left to look at.